Ever catch yourself wondering what happens after you hit save? Like,
Uh-huh.
really, where does all that data actually go?
Yeah.
Well, get ready to dive deep because today we're cracking the code on file systems.
They're the unsung heroes, that's for sure.
Totally. They're the invisible force organizing our entire digital world. And we're going to uncover all their secrets.
Right from the bottom.
Yeah, imagine this. You walk into a library, right?
Oh, yeah.
But instead of neatly organized shelves and a helpful catalog system, you've got billions of pages
Oh, no.
scattered everywhere. Total chaos.
That sounds stressful.
Right. That's what your computer would be like without a file system.
Wow. I never really...
Luckily for us, some pretty brilliant engineering went into making sure that doesn't happen.
I'm glad someone figured that out.
Me too. So for this deep dive, we're turning to an excerpt from an operating system's textbook.
Always a good place to start.
It's actually surprisingly understandable, even for those of us who aren't, coding wizards.
It's amazing how much goes on behind the scenes that we never even think about.
It really is. And one of the first things that jumped out at me was this idea of a layered file system.
Layered?
Yeah, layered. Now, I know what you're thinking, Kick, right?
Maybe a little.
But bear with me. It's more like a well-coordinated team with each layer having a specific job to do.
Okay, that makes more sense.
And our textbook actually has this helpful visual, figure 14.1.1, that really brings it to life. It shows how each layer handles a different part of storing and retrieving your files.
Keeping everything running smoothly.
Exactly, like a well-oiled machine. So at the very bottom, the foundation, we've got the I/O control layer.
I/O control.
Yeah, this is the tech whiz that speaks fluent hard drive. It translates your commands into something the physical disk can actually understand.
Kind of like an interpreter.
Exactly. Then we move up to the basic file system layer.
Okay.
This one reminds me of those air traffic controllers, essential but unseen.
Keeping everything from crashing.
Right. It's managing this constant flow of data blocks, ensuring everything is stored and retrieved without a hitch.
And with so much data moving around, efficiency is key.
Absolutely. Now, moving up the ladder, we have the file organization module. If the I/O control is the interpreter and the basic file system is the air traffic controller, this layer is the meticulous librarian.
Oh, I like that.
It knows exactly where each piece of data for every single file is located on the disk.
Talk about organized.
I know, right? And on top of that, it keeps tabs on all the free space so it's ready to store even more stuff.
So that's how we never run out of room.
Well, almost never. But that brings us to the layer we're all most familiar with, the logical file system. This is where all the familiar faces hang out. File names, folders, even those pesky permissions.
The stuff we actually see.
Exactly. It's the user-friendly facade of this whole complex operation happening behind the scenes.
Hiding all that complexity. It's kind of brilliant when you think about it.
It really is. And it's this layered approach that makes the whole system so robust and flexible. But we've got to give a shout out to a crucial player we haven't even mentioned yet. Inodes.
Yeah, nodes.
Yeah, these little guys are like the stage crew of a concert. You never see them, but they're working tirelessly to make sure the whole show goes off without a hitch.
I never thought of it that way, but it's a great analogy.
Each file gets its very own inode, and these inodes are like index cards packed with vital information.
Like what?
We're talking file size, creation date, permissions.
It's all right there.
Yep. All that metadata, it's the behind-the-scenes info that affects how you interact with your files every day.
And we never even know it. I'm suddenly feeling very grateful for inodes.
Me too.
Imagine searching for one specific document in a sea of data without inodes.
That sounds like a nightmare.
Right. It would be impossible.
So how do these inodes actually help with something like, say, opening a file?
Well, imagine this. You need to find a specific restaurant.
You could wander around aimlessly hoping to stumble upon it.
Yeah.
Or you could use the restaurant's address, GPS coordinates, parking suggestions, all that extra info that makes finding it a breeze.
I know which one I'd choose.
Right. That extra info, that's basically what the inode's metadata is providing. It helps the system locate and access the file quickly and efficiently.
It's like having a shortcut.
Exactly. Now here's something I bet you've experienced. You delete a massive file, and it disappears instantly.
Yeah, it's oddly satisfying.
But then you try to copy that same file, and it takes forever.
That's always a buzzkill.
There's a reason for that. Deleting often just removes the inode's reference.
What do you mean?
It's like saying, hey, Sysme, you can reclaim this space now. but the data might still be there until it's overwritten by something new.
Oh, I see.
Copying, on the other hand, means actually duplicating all that data, which takes time. It's like the difference between taking down a sticky note versus moving an entire mountain of boxes.
Okay, now it makes sense.
It's amazing what you learn when you start digging into this stuff, right? But speaking of digging, did you know there's a whole world of different file systems out there?
Really?
Oh yeah. Our textbook mentions X3/4 for Linux, NTFS for Windows, and even specialized ones for things like CD-ROMs.
Wow, why so many?
Well, think of it like using the right tool for the job. You wouldn't use a hammer to saw wood, right?
That would be a disaster.
Exactly. Different operating systems and storage devices have different strengths and weaknesses, so file systems are tailored to optimize for those specific needs.
So like when a DVD wouldn't play on my old CD player?
Bingo. It wasn't just being difficult, it was probably a file system mismatch.
Who knew?
See, this is why we do these deep dives.
It all makes so much more sense now. I'm kind of amazed by it all, honestly.
Me too. But before we get too carried away, there's one more intriguing detail I've got to ask you about. Our source mentioned something called FUSI, and it sounds seriously next level.
UCCZ.
What is that?
Welcome back to the deep dive. We're jumping right back into the fascinating world of file systems. Last time, we explored the different layers.
Like a cake?
Well, sort of. We talked about the I/O control, the basic file system, the file organization module.
And how those inodes are the real MVPs.
Totally. But as we go deeper into this, I'm realizing it's not all smooth sailing in the digital world of data. Our source material mentions fragmentation,
Oh, yeah.
journaling, data recovery,
Sounds intense. Right, like what challenges do file systems even face?
and how do they deal with them? That's the big question. Let's start with fragmentation. Have you ever frantically searched for a lost TV remote?
Who hasn't?
Now imagine that, but you're searching for a single file, scattered in tiny pieces across your entire hard drive.
Oh, that sounds awful. And inefficient.
Exactly. It's like a giant jigsaw puzzle that's been constantly shuffled.
So how does fragmentation even happen? Is it just having too many files?
It's more about how files are written, deleted, and changed over time. Imagine you add pieces to the puzzle, you take some away.
Move some around.
Yeah. Eventually, you end up with gaps and spaces all over the place. New pieces don't fit neatly anymore.
So instead of having a file in one spot, it's fragmented, scattered all over the disk.
Exactly. Makes it much slower to access.
Because the system has to work harder to gather all the pieces. Like reading a book with chapters out of order. You can still follow along.
But it's not as enjoyable.
Definitely not. This is making me think about those old defragmentation tools we used to use. It's like digital tidying.
Exactly. But is fragmentation still a thing? With modern computers and those super fast SSDs?
That's a good question.
It's less of an issue with SSDs because they access data differently. But managing space is still important.
Especially with how much data we're all storing these days.
It's only getting worse, right?
Absolutely. But at least there are systems in place to keep things organized. Our source material also mentions something called journaling file systems.
Journaling.
Yeah, like keeping a diary, but for your computer's data.
That's a pretty good analogy. Journaling file systems keep a record of every change made on the disk.
Like a digital paper trail.
Think of it as a system-wide undo button.
So if my computer crashes unexpectedly,
Or you have a sudden power outage,
which happens more than I'd like to admit,
the journal swoops in to prevent data loss. It's like a safety net.
that's a huge relief. Knowing there's a system in place to help recover data makes me feel much better. So the journal helps the system figure out what was happening before the crash.
Exactly. What operations were completed, which ones were interrupted. It helps ensure everything is consistent, minimizes the risk of data going MIA.
Like a digital guardian angel.
I like that.
Speaking of guardian angels, what about those times when things go really wrong? Hard drives failing, accidental deletions. How does data recovery even work?
It's complicated. But basically, deleting a file doesn't always mean erasing the data itself. Remember those inodes we talked about?
Of course.
Deleting often just removes the inode's reference. It tells the system, hey, this space is free.
So the data is still lurking around, like a digital ghost.
Exactly. Data recovery software can scan the disk, searching for these remnants of deleted files.
So it's like a digital detective.
Pretty much.
Right.
But the success rate depends on a lot of things. The type of storage device, the file system used, how much the data has been overwritten.
It's a race against time. No wonder they say act fast if you need to recover something.
Time is of the essence. The sooner the better.
This is blowing my mind. I had no idea so much was involved in things like saving or deleting files.
It's a testament to how ingenious file system design is. It's all about balancing performance, keeping things safe, and making sure your data isn't going anywhere.
It's like a high-tech juggling act.
A very, very important one. And speaking of juggling, things are about to get even more interesting.
Welcome back to the show. We're wrapping up our deep dive into the world of file systems, and I have to say, this has been quite a journey.
It really makes you appreciate the hidden complexity behind everything we do on our devices.
Totally. In parts 1 and 2, we went from the nitty-gritty of hard drive communication to the art of data recovery.
We saw how file systems keep our digital lives from becoming completely chaotic.
Right. But here's the thing. Our digital lives aren't confined to just one device anymore. We've got cloud storage, shared documents, devices galore.
That's a lot to keep track of.
It really is.
Yeah.
So how do file systems keep pace with this interconnected world?
That's where distributed file systems come in. Yeah, imagine a file system that's not limited to just your computer, but spans multiple devices, servers, even entire networks.
Okay, so not just one location, but spread out.
Exactly.
Yeah.
And it's all connected, providing a seamless experience for the user.
That sounds incredibly complex.
It is, but also incredibly efficient. Distributed file systems use sophisticated networking protocols and algorithms to make it all work.
It's like magic. I can access a file on my phone that's actually stored on a server miles away.
That's the beauty of it. Think of it like this. Instead of having all your books on one shelf, you have them distributed across multiple libraries.
Okay.
But you still have a way to find any book instantly, no matter which library it's in.
So it's all about accessibility and reliability, even if one part of the system goes down.
Exactly. That's a major advantage of distributed file systems. They're incredibly resilient. Plus, there's the scalability factor.
Scalability.
As your storage needs grow, you just add more nodes to the distributed system.
So it can handle massive amounts of data.
Precisely. Which is essential for things like cloud computing and big data applications.
This is all starting to make sense, but I have to ask, with all this data floating around, is security a concern?
Absolutely, and it's a major priority for distributed file systems. That's why they utilize things like encryption and authentication protocols.
To make sure only authorized users can access the data.
Exactly. And there are audit trails to track who accesses what and when. It's like having a highly trained security team guarding your information across a vast network.
Wow, it's amazing how much thought and engineering go into something we rarely even think about.
It's a testament to the brilliant minds working behind the scenes to make our digital lives possible.
It really is. So, next time you hit save or share a file, remember those unsung heroes. The file systems diligently organizing our data and keeping it safe.
They're the backbone of our digital world, even if we don't always see them.
And on that note, we've reached the end of our file system deep dive. We hope you've enjoyed exploring this fascinating world with us.
Ever hit save on a document and wonder where it really goes?
Mm-hmm.
I mean, we know it's stored somewhere on our computer,
Right.
but what's happening on a deeper level?
Yeah.
That's what we're diving into today.
Oh.
The often overlooked, but incredibly important world of file systems.
It's like opening up the hood of your computer and seeing all the intricate parts working together.
Oh,
Except instead of gears and belts, we're dealing with bits, bytes, and some seriously clever organization.
And our source material for this deep dive is fascinating. A section from an operating systems textbook that gets into the nitty-gritty of how file systems actually work.
Wow.
It's amazing how much complexity goes into something we use every single day without even realizing it.
It's easy to take for granted, right? You
Yeah.
click save and boom, your file is stored. But behind that simple action is a whole symphony of processes.
Wow.
Designed to ensure that your data is organized, accessible, and persistent.
Okay, so let's start with the basics.
Sure.
What exactly is a file system? I think a lot of people probably picture a hierarchical structure
Right.
with folders and files,
Yeah.
but it's obviously a lot more than that.
It is. Imagine a massive library.
Okay.
But instead of books, we're talking about potentially millions or even billions of files.
Wow.
The file system is like the super organized librarian. It's responsible for keeping track of where everything is stored, who has access to it, and a bunch of other crucial information.
Our source material dives deep into the different types of information a file system manages.
Okay.
And it's not just what you'd expect. Of course, it stores the contents of our files, but it also keeps track of things like boot instructions for the operating system,
Okay.
and how much free space is left on our hard drive.
Exactly. And it's not just about what's stored, but how it's stored.
Right.
The textbook talks about both on-storage and in-memory structures,
Okay.
which might sound a bit technical, but it's actually a really clever way to balance speed and reliability.
Okay, let's unpack that a bit.
Sure.
On storage makes sense. That's our files physically stored on the hard drive, or SSD, right?
Precisely.
Yeah.
It's the long-term memory of your computer.
Gotcha.
But imagine if every time you needed to access a file, your computer had to go all the way back to the hard drive and read it from scratch.
Right.
That would be incredibly slow,
Yeah.
right?
Yeah, especially with today's massive files. It would be like searching through a whole library to find one specific page.
Exactly. And that's where in-memory structures come in.
Okay.
These are like little shortcuts or caches that the operating system keeps in RAM.
Right.
Your computer's much faster, but temporary memory.
Okay.
It stores frequently accessed file information there, so it can be retrieved much more quickly.
So it's like keeping your most used cookbook on the counter instead of having to go all the way back to the bookshelf every time you need a recipe.
That's a great analogy. It's all about optimization.
Right.
The operating system is constantly working behind the scenes to make sure you can access the files you need as quickly as possible.
That makes a lot of sense.
Yeah.
So we've got this system for storing files in a way that's both organized and efficient. But what happens when we actually want to create a new file?
Yeah.
Let's say we've just written the next great American novel, congrats by the way, and we hit save. What's the next step in this fascinating journey?
This is where the logical file system comes into play.
Okay.
The textbook describes it as the brains of the operation,
Right?
and it's a really apt description.
Okay.
The logical file system is responsible for understanding the overall structure of all the directories and files on your computer.
Right, so it's not just randomly throwing our novel onto the hard drive somewhere.
Right.
There's a method to the madness.
Absolutely. And to keep track of everything, the file system uses something called a file control block,
Okay.
or FCB for short.
Gotcha.
Think of it like a library card for your file.
I love that analogy.
Yep.
So instead of a due date and a stamp, our file's FCB contains what?
It holds all the essential details about the file name, its location on the hard drive, the date it was created, who has permission to access it, and more.
Wow.
It's like a little passport for your file that tells the operating system everything it needs to know.
Fascinating.
Yeah.
So when we hit save on our masterpiece,
Yeah,
the operating system doesn't just store the words.
right.
It creates this FCB, this library card, and then carefully places it within the overall directory structure.
Exactly. The directory structure is essentially a constantly updated table of contents for your entire hard drive.
Okay.
And this is actually where different operating systems have their own unique approaches.
Oh, tell me more. Our source material actually mentioned this.
Okay.
Something about UNIX and Windows handling directories differently.
It's a fascinating bit of computer science history. You see, in UNIX-based systems like Mac OS or Linux, directories are treated just like any other type of file.
Yep.
They have their own FCBs and are stored within the file system hierarchy.
Right.
But Windows took a different route.
Interesting.
They have a separate system for managing directories.
So even at this fundamental level, there's already this fascinating divergence in how different operating systems tackle the same challenge.
Exactly. And each approach has its own set of advantages and disadvantages, but that's a topic for another deep dive, perhaps. For now, the key takeaway is that creating a file is more than just writing data. It's about meticulously updating this intricate system of records and metadata.
It really makes you appreciate the complexity of what's happening behind the scenes. But let's
Yeah.
move beyond creation. What happens when we actually want to open and use that file? Our novel is written, saved, meticulously cataloged by the operating system.
Right?
And we're ready for that grand open file moment.
Okay.
We double-click the icon.
Yeah.
What's next in this intricate dance of bits and bytes?
This is where things get really efficient.
Yeah.
Remember that open file table we touched on earlier?
Right. It's how the system makes sure two programs don't try to edit the same file at once,
Exactly.
causing a digital meltdown.
Precisely.
Yeah.
So first things first, the operating system checks this table to see if the file's already open.
Okay.
If not, it adds our novel to the list
Right.
and generates a unique key for it, what's called a file descriptor.
A key, like a backstage pass to access the file's content.
Exactly.
Okay.
This file descriptor is a temporary identifier, a way for the operating system to manage access while the file is open.
Okay.
It's like handing your ticket to an usher to find your specific seat in a theater.
And this theater
Yeah.
is Yeah, exactly. Is the entire novel loaded into RAM at this point?
That's where things get really clever.
Okay.
Remember that impressive 85% cache hit rate our textbook mentioned for BSD U99X?
Yes.
That's the operating system's way of saying it's already one step ahead.
So parts of our novel might already be hanging out in RAM even before we open it.
Quite possibly. The operating system uses a mechanism called caching,
Okay.
where it keeps frequently accessed data in RAM,
Right.
which is much faster to read from than the hard drive.
Right.
It's like keeping a frequently used book on your desk instead of returning it to the bookshelf every time.
Okay, that's incredibly efficient.
Right.
So we've got our file descriptor, our backstage pass,
Right.
and the operating system is pulling data from the cache or the hard drive as needed.
Yeah.
Is that basically it?
Yeah.
We're free to write the next chapter.
Almost.
Okay.
Keep in mind, every time you make a change to the file,
Right.
like adding a brilliant plot twist, those changes are first stored in a temporary buffer in RAM.
Makes sense.
Yeah.
Got to keep things snappy while we're in the creative flow.
Right.
But those changes aren't permanent until we hit save again.
You got it. When you save, the operating system takes those buffer changes
Okay.
and writes them back to the file's actual location on the hard drive, updating its permanent storage.
So there's this constant back and forth,
Right.
a delicate balance between speed and ensuring our data is safe and sound.
Precisely. And don't forget our trusty FCB, the file's library card.
Right.
When you save, the operating system updates the FCB on the hard drive too,
Go.
recording the last modified date and other relevant metadata.
It's amazing how much detail goes into each step of the process.
Right.
It's like an intricate choreography of data management. It's amazing how much is going on behind the scenes, isn't it?
It really is.
We've covered a lot of ground in this deep dive, haven't we?
We have. It's really just the tip of the iceberg, though.
Right. We focused on the basics.
Yeah, it's the fundamentals.
Creating, saving, opening files.
Mhm.
But there's so much more to file systems than that.
Oh, absolutely. I mean, file systems are constantly evolving.
Right.
The demands of modern applications like massive databases, cloud storage, real-time collaboration, those all present new challenges and require innovative solutions.
And we didn't even have time to get into what happens when things go wrong.
Right.
Data recovery, file fragmentation, disk errors.
Exactly, all things.
Those are deep dives in themselves.
They are. Each one could be a deep drive of its own.
Speaking of which, that actually makes me think,
Yeah.
if I delete a file, is it really gone?
That's a great question.
Or is it just like hiding somewhere?
Well, it's a little of both, actually.
Okay.
When you delete a file, the operating system doesn't immediately erase the data.
Okay.
Instead, it marks that space on the hard drive as available for reuse. So the data's still there.
So it's like,
It's like putting a vacant sign on a hotel room.
oh, I see. Okay.
It's only a matter of time before something else moves in.
So if I act quickly enough, there's a chance I could get that deleted file back.
Exactly. There are data recovery tools that can scan those vacant areas of your hard drive and potentially recover the data.
Wow.
But the longer you wait, the higher the chance that space is going to get overwritten with new data.
Making it much harder to recover.
Exactly.
Fascinating. So it really is a race against time.
It can be.
And understanding how file systems work
Right.
gives you a head start if you ever need to recover something you accidentally deleted.
Knowledge is power.
That's right. Well, unfortunately, that's all the time we have for today's deep dive into the fascinating world of file systems.
This is a fun one.
I had a great time. Thanks for joining me today.
Anytime.
And to all our listeners out there, keep exploring, stay curious, and we'll see you next time.
Okay, remember those old spinning hourglasses? The ones that would pop up on your screen every time you tried to copy a big file and just make you question your life choices?
A universal symbol of impatience, for sure.
Right. Like just a little digital thumbs in the face. Hold your horses, buddy. This might take a while. And it's funny how much faster things are now, but at the same time, it feels like we're always chasing that next level of speed.
It's true. Always pushing the limits. But you've hit on something interesting, though. No matter how fast our processors get or how much RAM we cram into our devices, there's always this bottleneck.
Yeah.
And it usually comes down to storage.
It's like having a shiny new sports car, but it's stuck behind like a lumbering school bus on a narrow road.
Exactly.
No matter how much horsepower you have under the hood, you're not going anywhere fast.
You're not.
But why IS storage, the perpetual slowpoke in the digital world?
So fundamentally, it comes down to the difference between electrons and, well, physical stuff.
Okay.
Your CPU, it's all about electrons zipping around at nearly the speed of light.
Right.
Storage, on the other hand, Even those super fast SSDs involves physical limitations. Things spinning, heads moving, data being physically written or retrieved. It's a much more hands-on process.
Okay, so no matter how fancy our storage tech gets, there's always going to be that speed gap compared to the lightning-fast world of the CPU.
Exactly. Which is why efficiency is the name of the game when it comes to storage. Think about it like organizing a messy closet. If everything's just tossed in there haphazardly, it takes forever to find what you need. But if you take the time to organize it, everything has its place, you can find things much faster.
Right. Oh, absolutely. I'm a big believer in a well-organized closet, or at least aspiring to be one. But how does that translate to the digital world of ones and zeros?
Just like your closet organization system, efficient storage is about two things: space and speed.
Okay.
Let's talk space first. The text mentions this clever trick UNIX uses called inodes. Now, an inode is basically like an address label for each file and folder on your drive.
So it's not the actual data, but more like a roadmap to find that data.
Exactly. And UNIX, being the clever system it is, pre-allocates a small amount of space for these inodes, even when the disk is brand new and empty.
Seems a little counterintuitive, doesn't it? Like reserving parking spots at an event before anyone's even arrived.
That's a great way to put it. But here's the thing. Having those inodes ready to go up front actually speeds up file creation and retrieval later on.
Okay.
Because when your computer needs to create a new file, it doesn't have to scramble to find space for that address label.
Right.
It's already there, ready and waiting.
So a little upfront investment in organization pays off big time in the long run. Makes sense. But what about the speed side of things?
That's where clustering comes into play.
Yeah.
Imagine you're packing a suitcase. You don't want to just throw things in randomly, right? You try to put the bulkiest items at the bottom, fit smaller things around them, make the most of the space.
Oh, I am the queen of packing cubes and strategic suitcase organization. Otherwise, you end up with a jumbled mess and never enough space.
You've got it. And that's what clustering does for your hard drive. Instead of scattering bits and pieces of a file all over the place, it groups data together in blocks, or clusters. Larger clusters are more efficient for big files, like that 4K video you're trying to edit. Smaller clusters are better for lots of little files, so you don't waste space.
It's like choosing the right size packing cube for each item in your suitcase.
Precisely. And some operating systems, like BSD UNIX, actually vary the cluster size as a file grows. It's like starting with a small packing cube and upgrading to a bigger one as you add more stuff.
Now that's some next level digital organization right there. But I have a confession. I'm guilty of prioritizing convenience over organization sometimes.
Yeah.
Like, my desktop is a constant work in progress, shall we say. Do we ever intentionally make things a little less efficient in the name of convenience in the digital world?
We do, all the time. It's a constant trade-off in system design.
So tell me about the price of convenience. When do we make those deliberate sacrifices in efficiency?
Well, let's think about a feature we take for granted: keeping track of the last access date for a file.
Right.
Seems like a small thing, right?
Yeah, super useful for finding things you were recently working on.
Absolutely. But every time you open a file, the system has to update that last accessed date, which means writing data.
Okay.
So even if you just opened a file for a split second, that still takes up resources and, yes, can even slow things down a tiny bit.
Wow, those hidden costs. I guess even in the digital world, there's no such thing as a free lunch.
Exactly. And sometimes those costs are bigger than we realize.
Yeah.
Remember when hard drives used to be laughably small? Like 32 megabytes was considered a lot of storage space?
Vaguely. Mostly because my phone could hold a small country's worth of data these days.
Exactly. Back then, MS-DOS was king, and its file system was designed around those tiny storage sizes. They used what we call 32-bit pointers, which basically means they had a limited number of addresses for files. Worked great at the time.
Yeah.
But as hard drives got bigger,
They hit a wall. I'm sensing a butt coming, and I don't think I'm gonna like it.
it wasn't pretty. Those 32-bit pointers could only handle files up to a certain size, anything bigger. And the system just didn't know what to do with it.
So what happened? Did they just invent bigger pointers?
Essentially, they had to completely overhaul the file system to use larger pointers, which caused a whole lot of headaches for users. It's a great example of how a seemingly small technical decision can have a huge ripple effect.
It's fascinating, really. All this complexity hidden behind the simple act of saving a file. It makes you appreciate those little spinning hourglasses even more, doesn't it?
There's a lot more going on behind the scenes than most people realize.
Yeah.
And it gets even more interesting when we start talking about caching, the ultimate weapon against the tyranny of slow storage.
Caching. Okay, now you're speaking my language. This sounds promising. Tell me more. All right, we're back, ready to dive into the world of caching. Sounds like this is where things get really clever.
Yeah, you could say that. Caching is all about working smarter, not harder. Like having a team of tiny librarians in your computer constantly fetching the books, or, in this case, data that you're most likely to need next.
Okay, I am here for any and all librarian analogies. But actually, before we get too far, we spent a lot of time in the last segment talking about how computers read data. What about when we're writing files? That seems like a whole different ballgame, with a lot more potential for disaster if something goes wrong.
Oh, you're absolutely right. Writing data comes with a whole new set of challenges. When you're reading, the system can be a bit more relaxed. It can use tricks like read ahead, where it grabs a bit more data than you actually asked for, just in case you need it next. But writing is a more delicate operation.
Because if your computer crashes mid-save, bad news.
Exactly. So when it comes to writing data, there's this constant balancing act between speed and safety. The text mentions synchronous and asynchronous writes, and it basically comes down to how much risk you're willing to tolerate for the sake of speed.
Okay, I'm intrigued. Walk me through this high-stakes game of digital risk and reward.
All right, so think of a synchronous write, like sending a package with signature confirmation. You have to wait for the delivery person to get your signature, and only then do you know for sure that the package has reached its destination. Slower, but secure.
So that's what's happening when I hit save, and that little spinning icon holds me hostage until it's done. My computer is playing it safe, making absolutely sure everything is written to the disk before moving on.
Precisely. Now, an asynchronous write is more like dropping a letter in the mailbox. You assume it'll get delivered, but you don't stand there, like waiting for the mail carrier to pick it up. The system takes your data, says, trust me, I'll get this written to disk eventually, even if it hangs out in the cache for a bit first.
Way faster, but riskier if the system crashes before that data makes it from the cache to the hard drive, like hoping that letter doesn't get lost in the mail.
And that's why systems use synchronous writes strategically, usually for things like updating file metadata or in databases where you absolutely need to make sure data is written in the correct order. But for most everyday tasks, asynchronous writes offer a good balance of speed and risk.
Wow. It's fascinating how much thought goes into these trade-offs. We talked about read ahead for sequential access, like watching a movie. Are there other ways computers optimize for these patterns?
Absolutely. The way we use our computers directly influences how these systems evolve. Remember we were discussing Solaris and its different caching algorithms? Well, they also implemented something called free behind for sequential access.
Okay, free behind. It sounds ominous. Like something you'd say to a friend before daring them to do something reckless.
Not reckless at all, actually. Imagine you're reading a physical book, one page after another. You don't need to hold the entire book in your hands at once, do you?
That would make for a very tiring reading experience. I usually just hold on to the page I'm on, maybe the one before, just in case.
Exactly. Free behind is like that. Once the system is confident you're done with a certain block of data, it frees up that space in the cache, making room for new stuff.
So it's like clearing the dishes between courses at a fancy dinner party. You need those plates for the next delicious course, not the one you already ate.
A very elegant analogy. And then there's the read ahead we mentioned earlier. The system tries to predict what you'll want to read next and prefetches it from storage, just in case. If its guess is right, you get that data instantly.
It's like my computer is reading my mind, or at least trying to anticipate my next move. Are we entering the era of psychic computers? Should I be concerned?
Let's not get ahead of ourselves. But it is fascinating how these systems are constantly analyzing our behavior, looking for patterns that can help them shave milliseconds off our wait times.
Milliseconds add up. But it sounds like there's a difference between optimizing for sequential access, like watching that movie, versus random access, like, say, jumping between different files in a project.
You're right. What works for one situation might not be ideal for another. It's like the difference between reading a novel cover to cover and flipping through chapters in a textbook. Different tasks, different needs. And that's why these caching strategies are constantly being evaluated and refined.
Like a never-ending game of digital chess with the computer trying to stay one step ahead. And it all comes back to that fundamental speed gap we talked about earlier.
Exactly.
Huh.
We can be clever with caching and optimize for different usage patterns, but at the end of the day, there's still a limit to how much we can cheat physics. It's like that sports car stuck behind the school bus. No matter how good the driver or how efficient the route, it's still going to be held back by that lumbering behemoth.
So even though storage technology keeps getting bigger and faster, we're still bumping up against those fundamental limits.
We are. And that brings us to a pretty big question. What happens as the amount of data we generate continues to explode?
Okay, I'm listening. This sounds like it's going to be good. We're back for the final part of our deep dive into the wild world of computer storage. And that cliffhanger has me a little worried. Are we, like, headed for some kind of digital data apocalypse? Is that what you're saying?
Apocalypse might be a tad dramatic.
Okay.
But it's true. The sheer volume of data we're creating these days is, well, it's kind of mind-boggling when you really think about it.
Yeah.
High-definition videos,
Right.
massive data sets for machine learning, sensors collecting data every millisecond.
Yeah, it's like we're all trying to fill the Grand Canyon with digital sand, like one grain at a time.
And that's just the tip of the iceberg, really. Wait till we've got self-driving cars everywhere, virtual reality worlds to store, the Internet of Things exploding with sensors.
Okay, I get it. We're creating a lot of data. But, I mean, the answer's always been bigger, faster storage, right?
It has been, but we're getting to a point where faster and cheaper might not be enough.
Yeah.
We need to fundamentally rethink how we handle this absolute deluge of information.
So what are our options? Are we talking like crazy sci-fi solutions, data crystals, storing information on atoms?
Hey, never underestimate human ingenuity, right?
That's true.
But even with those futuristic possibilities, we've got to figure out how to deal with today's reality. How do we prioritize what needs to be stored lightning fast versus what can be archived a bit more leisurely? How do we design systems that can handle this kind of exponential growth? These are big questions.
Yeah, it's like we're playing digital Tetris, but instead of blocks, it's like the entirety of human knowledge and experience. And the screen just keeps getting bigger and faster.
And that's what makes this such a fascinating field to be in, honestly. Because there's so much opportunity for real innovation. Not just to make things faster, cheaper, but to fundamentally change how we think about storing and accessing information.
So our need for speed, it might actually be pushing us toward a completely different way of thinking about data storage.
It's already happening. We're seeing new storage technologies emerging, more efficient algorithms, even AI being used to optimize data storage and retrieval. It's a really exciting time.
Wow. You know, I have to admit, when I hit save on a file, I don't usually sit there and like ponder the intricacies of data storage. But now I realize there's this whole hidden world working away behind the scenes to keep our digital lives running.
It is, and it's a world that's constantly evolving, which brings us back to that spinning hourglass from the beginning of our conversation.
Oh no, not the hourglass.
What once felt like an annoyance, like a symbol of slow, clunky technology. You know, one day we might look back on that with a certain fondness, a nostalgia even, a reminder of a simpler time.
Before we were drowning in data.
Exactly.
I'm almost starting to miss that little spinning hourglass. Almost.
Yeah.
But for now, I'm pretty grateful for the quiet hum of my hard drive, you know, diligently storing all my digital treasures.
As are we all. But who knows what the future holds, right? What innovations are you most excited about when it comes to the future of data storage? Head over to our website and let us know. We'd love to hear your thoughts.
That's all for this deep dive, everyone. We've journeyed from the nitty-gritty of how data is stored all the way to the mind-blowing challenges of managing a world overflowing with information. But most importantly, I think we've uncovered some fascinating and honestly kind of unsettling questions about what the future holds for data storage.
Until next time, happy storing, everybody.